All right, the good news is we can use integrating factors to solve even more general ODE. And in fact, what we'll do, we'll solve ODE of the form. So not y prime plus ay equals a function of t, but this time y prime plus p of ty equals f of t. So same thing as before, but this time the coefficient of y can depend on t. And of course, I chose p of t because of Peyam Tabrizian. In particular, let's try to solve the following ODE. Example, y prime plus 3t squared y equals 6t squared. And it's still the same idea. You multiply it by an integrating factor to use a product rule. So step 1, integrating factor. But the big caveat here is, I love using that word caveat, is that we don't multiply it by e to the 3t squared. So don't multiply by e to the 3t squared. It's not the same thing as e to the at anymore, because it's a more general equation. However, the integrating factor is not too far off. So here's a general formula, which I'll prove in the next video. So for y prime plus Peyam Tabrizian y equals f of t, you multiply by. It's still e to the something, but in this case, e to the antiderivative of p of t. And it's kind of cute because it kind of looks like Yelp, because e to the integral of p of t is like e to the LP. But in any case, so in this case, here, what is p? It is 3t squared. And our f was 6t squared, which doesn't matter here. And so what is our integrating factor? So integrating factor, well, it's simply e to the integral of p of t dt, which is e to the integral of 3t squared dt, which just becomes e to the t cubed. And you might be like, Peyam, where's the constant? The good news is we don't need the constant here because we just need one integrating factor. We just need one function that helps us solve the problem. Okay, the good news is the rest is the same thing. So we still multiply by e to the t cubed. E to the t cubed. So remember, our differential equation was y prime plus 3t squared. Y equals 6t squared. Now let's just multiply all sides, but e to the t cubed. E to the t cubed, e to the t cubed. So plus 3t squared y equals 6t squared of this. And the cool thing is, the same fact is true. Multiplying by the integrating factor turns the left-hand side into the product rule. So if you apply the product rule, this gives you et cubed y prime equals 6t squared e to the t cubed. And by the way, this will always be true. If you do the integrating factor method correctly, it will always be integrating factor times y prime. Okay, and then the rest as usual. So e to the t cubed y becomes integral of 6t squared e to the t cubed dt. And here you see a function and its derivative. That's a great time to use u sub. So u is t cubed, and then du is in fact 3t squared dt. So in this case, 6t squared dt is just 2 du. And then what we end up getting is e to the t cubed y. I think it just becomes integral of e to the u 2 du. And that becomes 2e to the u plus c. And that's 2e to the t cubed plus c. And then last but not least, dividing by e to the t cubed, you get y is e to the minus t cubed times 2e to the t cubed plus c. That becomes here y is 2 plus c e to the minus t cubed. That's all she wrote. But just two little remarks. So the first one is, well, here we learned two methods. We had the e to the at method and the Yelp method, e to the integral of p of t. It turns out the e to the at method is just a special case of this general method. So you only need the general method from now on, really. Because for y prime plus ay equals f of t. Let's see what happens when we apply this formula. So the integrating factor is e to the integral of a dt, but an antiderivative of the constant a is just at, okay, plus c, but we ignore the constant. So e to the at. So the idea is really the method I presented now is more general. So you don't even need to remember the e to the at method. And so what's left for today is simply just proving this. Why do we get e to the integral of p? And then just doing one more example.